Hello and welcome to Homework 1, Part C. In Part C, Part 1, we are going to derive the system of ordinary differential equations that describe the time-varying concentration of n stirred tanks in series, which is essentially a CSTR. Then for Part 2, which has B, A, and B different parts, for a total volume of a 1 liter distributed over 20 tanks, which would be n in this case, and a flow rate of 0.1 liters per second at steady state with a concentration of 0.1 molar flowing through the system, a rectangular pulse of concentration 0.5 molar enters the first tank at 1 second and reverts back to 0.1 molar at 2 seconds. Modeling the boundaries of this rectangular pulse as a scaled/time-shifted sigmoid function with scaling of 50, which is essentially how fast this function is going to take place. Simulate the response of the system. In particular, show, for Part A, a plot of the time-varying concentration on the x-axis, which is time, of the 20 stirred tanks, and B, plot of the concentration profiles. X-axis is a fractional traversal across the 20 tanks, ranging from 0 to 1 at varying times. So what I'm going to do is first I'm going to derive our system of ODEs on the board behind me, and then I'm going to code out this problem on Google Colab. And first we're going to set everything up and write down our ODEs before going and creating our first plot and then our second plot. So I just spoke about and kind of explained problems homework 1C, and now we actually have to derive the equation. So what it's asking us is to calculate or kind of have different equations for how we can solve when we plug a lot of CSTRs together in series to kind of stipulate or simulate what a plug flow reactor should look like. So we have two different equations we're going to have to write for the system. One for our first tank, which we're calling tank 0, and then the other equation is for the rest of the tanks. C0, or tank 0, is special due to the fact that it has Ca in. While all of these concentrations, such as an example where it says Ca naught, it's going to be Ca1, well, these have the unique aspect of kind of flowing through. This one is our original, which is why we need to create kind of two mass balances for it. So if you've watched homework video 1B, the mass balance phase is going to be very similar. So for our first mass balance, we're going to do dV times C naught equals, or over dt, equals what comes in over minus what comes out. So what comes in is, another thing is we're going to say Q is the same. So, Q equals the same because it's the same flow rate, it's the same volume. So it's just going to kind of push its way through. It's going to be the same. So equals Q, then we're going to do CA, so what's coming into the tank? CAN minus CA naught. And then we're going to, because V is constant, we're going to take that out. Then we end up getting dC naught for the first tank over dt equals Q over V CAN minus CA naught. So this is our first mass balance for our first tank. And now we're going to write the next few. So because these are the same, the reason the next ones are the same is because we can say, oh, it's CaO, Ca1, Ca2, Ca3, Can. But we can't do that because Can is constant. It's the exact same. So we're now going to do dV, and we're going to do, let's just do C1, Ca1, or tank 1. And we can actually replace this with N, theoretically. But we're not, for now. Equals Q, because again, Q is the same. And we're going to do, so this is going to be what's coming in, it's going to be Ca naught minus Ca1. What goes in minus what comes out. And this process, or this formula, well, we're going to take V out and just rewrite it again. Typo. dC over dt, for example, for 1, we can do this for n, equals Q over V, constants, times CaO minus Ca1. So what we can end up doing is essentially dCn over dt, so the concentration of n number of tanks, equals Q over volume, which we know, and we're going to do, let's see, D, not D, my bad, CA, this is going to be n minus 1, except there's going to be a limit. For example, we can't do this for CA0, because then it gives a negative, but we do this for CA1, because we do n minus 1, it ends up being CA0, which tracks, minus CAN. And this is the material balance for the rest of this series. Well, it depends, doesn't matter how many you have. I believe for this problem, we're going to have 20 tanks in one series, but it could be 50, it could be 1,000,000. But the more CSTRs you put in series, the more you can simulate perfect plug flow with no back mixing. So a perfect plug flow reactor, which is why we're going to start with 20, and we can move it around. I don't think we'll move it around in this problem, but you have the ability to just to simulate, oh, if we have a better reactor, you know, if our chemistry is this much smoother, what do we end up getting? So we end up having two different ODEs. This one right here, which is essentially this, just generalized, and then our original one. Sorry, just fixing a T there. And now I'm going to code this out in Colab. And there's two different graphs I'm going to end up making. I can't remember them off the top of my head right now, but I will see you there. Hi, so you just saw me derive the equations we needed for homework 1, part C. I just did part 1. So now we're going to go through all this fun stuff in which we distribute the volumes and have a great old time. So first, we need to calculate our volume. We have our total volume. Our volume per tank equals total top V divided by N, because this is essentially telling us how much volume per tank, and that can change depending on how many reactors we had. We also need to kind of create C naught, or our original cases for everything, equals NP dot full, and we need to do shape, and then fill value. So our shape is going to be, I believe it's an array, right? Or this, anyway, it's going to be N, as the shape is going to be N, and our fill value is going to be CA naught. So let's see if that actually doesn't break. And NP is not defined. NumP is NP. What do you mean the name NP? So is it just full? Or NP dot, it might be fill. I think it's fill. Alright, anyways, who cares? So now we're going to define our, how do we describe this? How do we call it? Define our pulse. So define pulse, and we're going to do CA equals 0.1, right, because we're originally at, plus X pit, and now we need to do 50 times T minus 1, because I said so. We do this 0.4, because times, what this is how high we want it, because we want this to get equal 0.5, right? 0.1 times 0.4 times, this is from 0 to 1, and we have 50, which is what is given here, because this is basically how the frequency, how fast it's going to go up, and then this is telling us to start it at time point 1, and then I'm missing something. Statements must be separated by new lines. No, I don't care. Minus the exact same thing, except we're going to subtract it by 2. And define pulse, and then we need to do time comma CA, or CA naught, whatever, and we need to then return this. I believe is how we're supposed to do it. So now, this probably isn't also going to work. Oh, it'll work, God willing. So now we need to start making a plot so we can kind of show that this was worked. If you guys, hopefully you can see this. So we're going to do, as we well know, we're going to do this first. T-plot equals NP dot linspace And then we're going to do 0 to 200. And how many? We have, let's double check. We have our stop, our start, our stop, and how many points? Let's do 500 because I can. Probably won't work, but now we need to do fig equals make under subplots. And I think I need to turn this into something. You know, this is just CA. We can do, let's see, we need to do like fig dot add, right, adds, where's it, dot scatter, underscore, NP is not defined, so is there something, like, why is that not working? Module numpy, okay, so maybe that is full, because it looks like that just wasn't running. Alright, perfect, so that worked. And now we can try this again. Hallelujah, hallelujah. Oh, that's why I didn't do that. So now we can do fig.add underscore subplot, in which we're going to do x equals time. So we're going to do x equals t plot, and then y equals pulse. And figure has no attribute add subplot. Makes, alright. There is something wrong with this going on here. I'm going to double check everything is working right, and I don't just have to hit this again and hope it works, because I did that before this had started, but that wasn't working for NumPy. So I'm going to double check this to make sure it's all right, because now I'm getting a little confused. Alright, so I found a few different issues that I was just kind of being dumb, and we're going to change this to CN, because that's essentially what we're tracking, and this really doesn't have any CA terms in it. All it is time. And another thing I, again, realized I messed up is this is supposed to be T2, which I even mentioned, because this is supposed to start at 1, end at 2, which is essentially what T minus is doing here. Alright, another thing is we do not want this to go on for 200 seconds. That would make no sense when it goes from 1 to 2. Fig make subplot, and we're going to add scatter, not subplots. That was add scatter. I think that's how it's supposed to be. And we're going to call this CN. Let me hit it with that real quick. We're going to do CN, and we're going to call this T-plot. And that should work. Or not. Oh man, what did I do? And then I think the next one I need to do is, let's see. Do you mean line? Well, yeah, I want to make it a line, so we're going to do method line. I don't think that's correct. Let's see. We need to call raise on invalid property error because we have to set it up to sync their casing. Syn x. Oh, maybe because, oh, that's my bad. X should equal t plot, not that. And then I want to make it into a line, but I don't remember how, so we're going to see if this works first. Perfect, it's already in a line. So you can see we go all the way up to 0.1, and it goes boosh. Or it goes from 0.1 to 0.5 at right around time equals 1 second. And then right around time equals 2 seconds, you can see it drops itself back down to, again, 0.1. So now that we have, this is our function for, let's see, for our sigmoid, as our pulse, now we can actually do what we coded. So now what we want to end up doing is defining our right-hand side. So we're defining our ODEs that we created originally. So we're going to define right-hand side. And, oh, that's not what I want to do. Right-hand side. And we're going to do time, of course. And what do we want? In time, we have a vector, So we have CA. We might have something else. We're just going to put CA in for now because that's what the right-hand side, if I wrote it down a little bit, this is what CA, or change in CA. So, looks like, so again, as I said, we're going to have two equations. And while it looks like I copied and pasted them, which I did, I am going to explain them because this is exactly what I derived. So, that needs to be indented. Concentration. I need to define a concentration, I believe. And I believe I have to return these as well. But I digress. So I'm going to explain this instead. So define our right-hand side. So our DC naught was essentially our equation for our original tank. So we have Q over V times C in T, so our original value at whatever time, because this is what we're coming in, minus C0. So this is our C in at a given time because it is a function, and it changes, minus C0. And C0 is our first tank, because if we look at an array, the number 1, like our first tank in the thing, is actually designated as 0. So that's what we have. And our next one is to the n, which I explained while we were deriving. So DC 1 to n, so our concentrations from 1 to our n amount of tanks, which in this case is 20, is Q over V times C, so the array, right, from 0 to negative 1 minus C to 1 to 0. So this is, it's going to start at 0, and then at negative 1, so the first in the opposite direction, minus C from 1 to infinity and beyond, essentially the end of the array. So it's going to start at the first thing of the array and go all the way through, minus something that's going to start at the first of the array and then go all the way through, which is what we had kind of spoke about. So C is undefined, but it's essentially talking to a, let's see, what does it say? Not defined, but it's essentially talking to the arrays that we have made, or we're going to make. So now we're going to define, or we're going to do a resolution equals, why is it like that? I have caps lock on, that's why. Res equals solve IVP, solve underscore IVP, and we're going to do RHS, time span. We're going to have to create a t-end, which I believe, because we used 10 up there, we're going to do t-end equals 10, which if we go through this and find that this doesn't work, we can change it. So we're going to do 0, comma, t-end, we'll put that in parentheses. What's our original y naught? Is we're going to say CA, is we're going to say it's CA naught. And then method, that's method, again, typos, me and I can't type, equals, we learned this from video 1B, it has to be uppercase, it gets mad at you, and then we're going to do dense output equals true. And let's see if this breaks. Okay, y naught must be one-dimensional, and CA naught is, however, C in is not. So I'm willing to bet we have to do this with C in. But I'm going to go and double check that because this is starting to get me turned around with all the CAs and CNs and Cs. So I need to go double check that. I'll be right back. All right, I found some issues that I'd made. So my first one is that I just called these C without actually changing the name, which is dumb. So, and then I need to, I gotta return like np.r underscore, and then I think that's it. I don't remember, but it's, basically we're slicing our arrays, but I think we do DCA and then DC that. See if this works. Okay, that works. Good God. So it also turns out one thing that was mad at this was y naught must be one-dimensional. So this is just a value. So we need to make it C naught, because this is not just for all of them. This is not just for one of them, it's for all of them. So we're going to do that. And then, let's see, what does it say? This is not a callable function. Hello. What's up? Alright then. But that's not working, so we're still, we go linspace, sorry, np.linspace, we're going to do 0 to tn to 20, or 200, and we're going to change our tn to 20 just because that's how many tanks we have. So now that we have that, and that, we're also, even though this isn't right, we need to do rs, I think we're going to call this cs equals sol.res, and then tplot, which is just kind of giving everything a value. Sol is not defined. Is it np solution, or is it res.sol? It might be res.sol, I believe. So you want the solutions somewhere. See where it breaks. Yeah, our class object is not callable. So that means I messed up something here. But I don't care, so I'm going to keep moving. Let's see, the next part we're going to do, so what do we do up here? How do we do this again? Figure 2 equals make subplots, boom, boom. And now we are going to want to do something funky for, it's called enumeration, so we're going to do like, I don't remember exactly how we want to do this, but it's CS or for something, let's do for something, we're going to enumerate, which is essentially counting how many iterations we have. So it's basically a good way for enumerate, and for CSI, I want to say for CS comma I, let's see, enumerate, and we need to also put something there, and yeah, so I'm going to be right back. I might cut that guy out, sorry, that's interesting. I need to figure out what I want to do here, because this is what is causing this issue, and then this should make sure everything here is right, and then figure out exactly how we want to make these plots, because what we're wanting to do is count them and then have, let's see, what does it say? We want to plot the time varying concentration x-axis of the 20 tanks. So basically, at what time each tanks have this amount of concentration in them. So yeah, we'll be right back. Sorry about that. I found at least one of my issues was over here for I, comma, CA in enumerate CS, our solutions. Basically want us to, for iterations in CA, count the different solutions. And also over here, the reason it's not a callable object is because it's an array, and I put it in parentheses, meaning it's not going to work like that. Like boom shakalaka. And now, I believe it should be indenting, so we can do fig2 dot add. Let's see, I messed this up last time. Dot add underscore scatter. X equals a time plot, and then Y should equal, what do we want? What is Y supposed to equal? We want to do method equal, or mode equal lines, and we also want to do name equal, this is where it gets tricky. We do like that, and then we do squiggly thingies, it should be like that. What I'm trying to do is index for the name should be whatever enumeration this is, and so we know that X is going to be our time, and on our Y, we want concentration. So I believe this should be CS, but I'm not exactly sure. So let's see what breaks. For I, oh, all right. So that worked. So now do we do why didn't it print? We just do fig 2. Oh man. I obviously broke something. So let's see. This should be F. I want this as tank. Well, so yeah, we have our tanks, right? This is what we wanted. However, I am obviously breaking something. So let's see, why is this not working? This tank 19, we do tank 0. Okay, so tank. That's interesting. It's doing a subtraction. It's like it's actually having like the subtraction from. It's like it's pulling the values from up here, but it's not actually doing any math. All right. I am going to mess around with this and try and figure out exactly why I'm getting a graph, right? But it's not what we want. So I'll be right back to figure this one out. So the only issue with this is that I put CS instead of CA. And I put CS because I was thinking we're solving, but we don't care about, well, we care about that because we're enumerating in terms of that, but we care about CA. And CA is what we're defining, so of course we should. And look at what you have here. We have our cascading effects. You can see in tank 0, we add our material in, and it slowly kind of cascades through, where our material is moving through each of the tanks, and much to a point where tank 20, or tank 19, finally starts to, because, well, we have 20 tanks, because it's tank 0 plus, doesn't count, right? Before tank 19 finally gets it back to steady state with around about 20 seconds. It's pretty good timing-wise. So now we're going to do part B, because this is actually the end of part A. So it's for, for I, x plot equals linspace, let's see, 0, 1, n. I'm going to do for I in range of 1 to 20. Let's do n just to see if this works. Yeah, I don't think that's right. But here, I just need to get that off my head. We want to time varying concentration, x-axis is time, 20 tanks. That's exactly what this is. We are showing the input, and then as you can see, concentration moves out through the tank at time equals 2.6. There is 0.2 concentration in tank A, and there is 0.2, almost 0.3 in tank 1, seeing that's moved on and being carried through the system. So let's see, xplot, NP, I always forget that. We are now going to just kind of brute force our way through this because I am a little lost as usual. And what the goal for this one is create a plot of the concentration profiles. X-axis is a fractional transversal across 20 tanks ranging from 0 to 1 at varying times. So that is exactly what this is. We are from 0 to 1 at n amount of times, 20. So now we're going to do, we also got to do this. Fig 3 equals make subplots. Did I type it wrong? Make underscore. Jeez, I'm never going to get this right at this point. Make subplots, and now we're going to do fig 3 dot add underscore subplot, add scatter, and now we're going to do x equals xplot. I'm recording, I think, which should be good. Xplot y is going to equal, okay, it's going to be brackets, I believe, to, because we want to start at the beginning. Now we're going to go all the way to, not 1. Or do we start, I'm trying to remember, 1 to I, right? So I in range of 1 to n. which is going to give us all except 1. And then we're going to do mode equal lines, and then we're going to do comma name equal, so for y, let's see, what do we actually want to name this? The concentration profile. So I believe it should be CA, or let's just call this CA. How do we do this again? Up here, my bad. F CA. I'm going to do ugly looking squiggly things. I index that, and then we're going to do this for, no, not that view. Fig3 dot add scatter. Scatter x equals x plot XPLOT y equals 200. No, because this is what we did up here, I believe, right? Because so what's going to happen up here is we're going to do like our numbers, and we're going to lose our last value. So what we're trying to do is just manually add our last one. So we do mode. I think, oh, we can do y equals -1. I think. Negative I. Why is this not happy? Oh, because that's why. Just keep hitting shift. It's either -1 or negative I. I believe -1, and then mode, again, I think it already comes in lines, but we still just designate this because we can. And then name equals CA, 200. And I don't think this is correct, but it'll break itself. Yeah, invalid syntax just for the original. Let's see. I believe I'm missing a comma there, but I need to double check because I want to make sure this syntax is correct. Because what we're doing is, for I in range of n, basically we're going to go from from 0 to 20, but we're going to lose our last value if I think I'm right. So that's why we need to, for at least for y values, this is why we're trying to add and manually this last part. It'll be, I believe it's 200, but again, I want to say it's 200. I need to go and double check this. After reviewing my notes, figured out a lot of things where I was going wrong, I had a wrong viewpoint. So what we're trying to do here, so 0, 200, 10, is we want to do this in steps of time. That's the whole point we're doing this. So it's going to be CS 0, 1. And then it's going to be, here's about CA, it's going to be time. We're doing this in steps of time. So every, time X, it's going to be time 200. It's going to be CS, -1. And we're going to see if this doesn't break. So this is what you should be getting. And really you need to break it down. So at time 0, the concentration is consistent, right? At time 0, there's nothing changing. Then you look at time 1, right at the end, right at the beginning, you kind of see this moving forward. You kind of see the slug moving through. Time 20, so time 20 is after the entire slug has kind of been moved into the tank. At the end is when the whole slug, you kind of see, if you keep going through, you can kind of see this slowly move throughout the system, right? See, just kind of like what we were showing up here, just you see the time throughout the system on the transversal, oh gosh, how did they describe it? On a fractional transversal across the 20 tanks. And that's exactly what you see here. Each 0.1 represents the tank. So as it goes across, you can just see how this system moves. So we're going to get rid of the first few. Now we're going to add the next few. And then, as you can see, we just slowly are moving this concentration, these variables, this right-hand side through it. At different times, it's showing how the concentration changes, which ends up solving part B of the problem. So at this point, we've gone through the derivation and the coding of the multiple different charts, and I'd like to say thank you for watching.